Today we'll be talking about the chapter solid state. Let us first talk about the different states of matter. As we know that we have three states of matter, that is solid, liquid and the gases. When I talk about the solid state, we say they have definite mass, definite volume as well as definite shape. In case of liquids, we say they have definite mass and volume, but they do not have the definite shape. While in case of gases, they don't have definite volume as well as the shape, but they have definite mass. In case of the particle arrangement, if you see, in case of solid state, we have a very close packing of the particles. That packing becomes intermediate or a little bit away from each other in case of liquids, and in case of gases, they are far away from each other. Therefore, the kind of the empty space which is available in between the particle, that empty space we call it as void space. We can see that void space is the lowest one in case of the solids. While in case of the liquids, that's more compared to the solids, and it's large in case of the gases. Since we have very tight packing in case of the solid particles, the intermolecular force of attraction is very high. In case of the liquid, it is intermediate, and in case of gas, the intermolecular force of attractions is almost negligible. So we are going to now concentrate on only solid state. The solid state can be classified into two types depending on the arrangement of the particles. They are classified into two types, that's crystalline and the amorphous. In case of crystalline, it's a homogeneous solid which the constituent particles are arranged in the definite repeating pattern. So you'll find a regularity in the structure in case of the crystalline solid. But this regularity will be absent in case of the amorphous. They don't have the regular orderly arrangement of the building units. Since in case of crystalline substances, they have a regular arrangement, you will always find in them there is a certain pattern repeated. Now if you can see in this particular pattern, this is the entire arrangement of all the particles in the regular shape. This arrangement is called as a crystal or a space lattice. But this crystal or a space lattice, if you see, some pattern is being repeated. Now you can see this particular pattern is repeated everywhere. So this smallest structural unit which is repeated everywhere, we'll call this as unit cell. So in case of crystalline pattern, there is certain pattern repeated everywhere, and that pattern we call it as unit cell. Amorphous, you will not find them irregular everywhere. You will also find them a small unit cell in them. But since that unit cell is not followed everywhere, so we call them as the amorphous or irregular arrangement of particles. That's why amorphous solids are known as pseudo-solids, or they are called as supercooled liquids. Now with respect to crystalline solid, we are going to study some terms over here. The first one will be talking about isomorphous. When I talk about the word morphous, the meaning of morphous is nothing but the structure. So iso means same and same structure. So two or more substances which are having the same structures are called as isomorphous of each other. For example, sodium fluoride and magnesium oxide. If you look at the composition, they have different composition, but the structure of these particles of the substances are same. So we'll call them as isomorphous of each other. The other term we are going to talk about, it's polymorphous or called as allotropes. As I said, morphous means structure. Now this is polystructural, that means different structure by the single substance. For example, the different allotropes of the carbon, that's diamond and the graphite. Diamond and the graphite both are made up of the carbon, but the arrangement of the carbon atoms in the structure are different. The next term I'll be talking about the anisotropy. For that, I want you to concentrate on this particular structure. Let's say for this particular substance, I'm measuring some physical properties. Let's say we are talking about the refractive indices. If I measure the refractive index in this particular direction, let's call this direction as AB, then this refractive index may be due to the large atoms coming across that particular direction. But if I measure this across this direction, let's call it as CD, we can see this refractive index may be due to the all small particles that is coming across. If I measure the same thing in this direction where I'm coming across one small, one large, one small, one large molecule, let's call it as EF. So every time, since the arrangement of particle is changing, the physical property will also change. So ability of the crystalline solid to change the value of the physical properties when measured in different direction, we call this particular ability as anisotropic. And this kind of anisotropy you will find most of the time with the crystalline solids. So let us combine all these different properties and distinguish between the crystalline and the amorphous substances. In case of arrangement, crystalline substances are regular while they are irregular in the case of the amorphous. Physical constant, that means we talk about the melting and the boiling point. You'll find crystalline substances always melt at the sharp temperature, whereas the amorphous solid melt over the range of temperature. In case of nature of substances, since there is a true arrangement of the particles in the regular manner, we call the crystalline substances as true solids, while the amorphous substances are called as pseudo-solids or called as the supercooled liquids. Nature, in the case of the arrangement as well, we can talk about the crystalline substances are isotropic or anisotropic in nature, while amorphous solids are isotropic. That means their property will remain same when measured in different directions. One of the important amorphous substance we'll be discussing over here, that's glass. We know that it's an optically transparent material, and around 800 types of materials available of glass material. We know that glass can be obtained by fusing silica at very high temperature. Now depending on other composition you add in this particular glass, we can have different types of glass. So let us discuss few examples over here. First we'll be talking about the quartz. When I talk about the quartz, it is just made up of silicon oxide. There is no other metal oxide present in this, and hence this particular quartz glass has a special quality that it cannot absorb the UV or infrared radiations, and hence we can use this kind of glass material to make the utensils if you are majoring or you are doing any study under the UV or IR radiation. So apparatus of that chemical test we can make it with the help of the quartz. Pyrex is a general glass which we use for making different utensils, that's consisting of 60 to 80% of silicon oxide, 10 to 25% of B2O3 and remaining Al2O3. Soda lime glass is consisting of 75% of SiO2, 15% of Na2O and 10% of copper oxide. Apart from this, we can also make different colored glasses. To have a red color, we can put some amount of gold or copper oxide. Yellow can be made with the uranium oxide. These all traces of oxides are added. Blue one, copper oxide or the cobalt oxide, and the green one, that is Fe2O3 or cobalt oxide. Copper oxide can be used. Next we'll be talking about the different types of the crystalline solids. Crystalline solids are classified into 4 types depending on the constituent particles. If the constituent particles are molecules, we call them as molecular solid. Here the force of attraction between the particles will be molecular forces. If the constituent particles are ions, we call them as ionic solid. If the constituent particles are metallic atoms, we call them as metallic solids. And if the constituent particles are atoms, we call them as covalent solids. Now in case of the molecular solid, as we discussed, they are consisting of molecules. Now molecules again can be of 3 types. They can be polar, they can be non-polar, or they can be hydrogen bonded. Now in case of polar, let us talk about, let's say, HCl. So HCl, when it is cooled under low temperature, the HCl will turn into the solid. Between HCl and HCl, there will be dipole-dipole interaction since it is a polar molecule. So we'll call this as polar molecular solid. In case of non-polar, we can take example of carbon dioxide. Carbon dioxide, solid carbon dioxide, that is dry ice. It's a kind of a non-polar molecular solid because between the CO2 and CO2, there are van der Waals forces or the dispersion forces, or also called as the London forces. Hydrogen bonded solids are those which are containing hydrogen, which is either attached to nitrogen or attached to fluorine or attached to oxygen. Because we know that in the periodic table, the highest electronegativity is found with the fluorine, the second rank goes to oxygen and third rank goes to the nitrogen. So whenever hydrogen is attached to any of these three atoms, the electronegativity difference becomes very vast, and hence the intermolecular force of attraction between these solids is hydrogen bonded. So under molecular solids, we have three types of solids: polar, non-polar or hydrogen bonded. But here one thing is to be noted, all these are molecular forces which are very weak, and hence the molecular solids have the lowest melting or boiling point amongst all the crystalline solids. Also, at room temperature, most of them you will find it in the gaseous state, except the water which is present in liquid state, and kind of solid like iodine which is present in the solid state. But rest of the solids you will find they exist in solid state at low temperature, so they are low melting, and since they do not have any free electron or the ions, they are bad conductor of electricity. The next type of solid, crystalline solid, is an ionic solid. They are consisting of ions, that is positively charged cations and negatively charged anions. And as we know that between positive and negatively charged cation and anion, there is electrostatic force of attraction, or we call it as ionic bond. These have a certain characteristic. They are hard, but they are brittle in nature. They are insulator in their solid state, but can conduct electricity in molten or aqueous state. On application of shear force. Now what is that shear force? Let us say we have this particular ionic solid piece. A shear force is something which you apply which is parallel to the length of the solid. Let us say if I have to separate these two layers of the ionic solid, I have to apply the force in the parallel direction to this. But if I apply that force in the parallel direction, since the cations and ions have the different sizes, these two layers will have a friction between the two when you apply the shear force on them. And since they have friction between the two, that particular crystal will undergo fracture in the structure. And due to the fracture, they do not have a property of malleability or ductility that we generally found for the metallic solids. Hence, we can say that ionic solids on application of shear force undergo fracture in the structure. The next type of crystalline solid is the metallic solid, which are consisting of the metallic atoms. When I talk about the metallic atom, in the metallic piece there are positively charged metal cations in which there are electrons, negatively charged electrons are embedded. So there is a force of attraction between the positively charged metal cation and negatively charged electron, and that force of attraction we call it as metallic bond. This metallic bond is very strong force of attraction, makes the metallic solid hard, high melting point. Now if I apply the shear force and if I have to separate these two layers will smoothly slide on top of each other, and since they have a smooth sliding on top of each other, they can be separated very easily. Hence the metal solids shows the properties like malleability and ductility. Alloy formation is possible for them, and definitely the metallic luster due to the mobility of electrons. The next type of solids we have, that's covalent solid, which are consisting of the atomic particles. These are giants or the network solids, and now they can be hard or brittle. That is totally dependent of the type of hybridization or a type of bonding which is available within them. Next, we'll be talking about the different arrangement of particles in the space. So when I talk about the different arrangement of particles, next we'll be talking about the brevis lattices, that is different arrangement of the particles in the space. Now Brevis is a mathematical scientist who has discovered the different arrangement of particles which is possible in the space. Now to define all these arrangements, we will be taking help of the three sides, that is A, B and C, and the angles between them, that is alpha, beta and gamma. Now before I start with the different descriptions of this particular particle, let us talk about the different arrangement of particles. If I say, if we have this particular cubical type of shape and only atoms are present at the corners of this particular cube, we call this arrangement as simple, or we call it as primitive arrangement. Apart from the corner atoms, if there is one more additional atom present in the body center, we call this as body center arrangement. Face center arrangement is the atoms present at the corner as well as the atoms will be present at the face centers, while the end center will be the corner atoms along with any two faces. That means this is, if I cover this as top, this will be bottom. That's called as end center. So we have 4 different type of arrangement available, that is simple, body centered, face centered and the end centered. Now depending on the descriptions of the different sides and the angles, we have classified the brevis lattices into 7 basic brevis lattices. When I talk about the cubic, where we have A is equals to B is equals to C, that means all 3 sides are same, but the angles will be different. Angles will also be same. Alpha is equals to beta is equals to gamma, that's equals to 90 degree. Under this category, we have 3 different arrangement, that is SCC, we have BCC and we have FCC. So that means total 3 arrangement possible for case of the cubic arrangement. In case of the next part, that is tetragonal, we have A is equals to B, but one side will be unequal, that is C. But alpha is equals to beta is equals to gamma, that's equals to 90 degree. Here we have 2 types, one is SCC and second one that we have is BCC. So we have 2 types under this. Next is orthorhombic, where we have A is not equals to B, not equals to C. But alpha is equals to beta is equals to gamma is equals to 90 degree. All 3 sides unequal, but still angles are equals to 90 degree. Here we have 4 types, SCC, BCC, FCC and the end center. So I will call it as ECC. So total 4 arrangement possible. In case of monoclinic, I will continue further. A is not equals to B, not equals to C. But alpha is equals to beta is not equals to gamma, that's equals to 90 degree. So here we have 2 types. One is SCC and the second one is the end center, that is ECC. So here we have total 2 arrangements. In case of triclinic, A is not equals to B but not equals to C. Even alpha is not equals to beta is not equals to gamma, that is not equals to 90 degree. So all 3 angles and all 3 sides are unequal. So under this category we have total only one type, that is SCC. In case of hexagonal, we have A is equals to B but not equals to C. While in case of angles, alpha is equals to beta is equals to 90 degree but gamma is equals to 120 degree. Here also we have simple arrangement, that's 1. In case of rhombic, we have A is equals to B is equals to C and angles will be alpha is equals to beta is equals to gamma, but that is not equals to 90 degree. Here the difference between the case of the cubic and the rhombohedral, they have 3 sides and 3 angles equal, but in case of cubic they are equals to 90 degree, but in case of rhombohedral they are not equals to 90 degree. So here under this type we have only again one type, that is SCC1. So total brevis lattices, if I count, we have 3 plus 2 5 plus 4 9 plus 2 11 12 13 14. So 14 brevis lattices total we have. But if the question comes how many basic brevis lattices, then we have 7. These are 7 basic one and they are categorized into subcategories. Total makes it 14 brevis lattices. Now out of this 14 brevis lattices, we'll be only talking about the 3 brevis lattices, that is of cubic type. We'll be talking about first SCC, then we'll be talking about the BCC and then we'll be talking about the FCC. In case of SCC, you can see there are 8 atoms at the corner of the cube. So we call this a simple cubic arrangement or we call this as primitive cubic arrangement. Now in case of coordination number, if we have to find out the coordination number for this particular structure, let us assume this particular atom. We can see this particular atom been surrounded by, on the back side we have one atom. So definitely when we have a 3D structure, in front side there will be one atom. At the top and at the bottom there will be 2 atoms. One atom is on left hand side, so there will be one atom on the right side. So top and bottom, front and back, left and right. So total coordination number for this atom becomes 6. In case of body center, just assume the atom which is present in the body center, which is being surrounded by 8 atoms at the corner. So here the coordination number becomes 8. While in case of this particular atom, which is, let us assume the face centered atom, This is surrounded by 4 atoms at the corner. There are 4 atoms at the back side with the face center. So similarly 4 more will come in the front side at the face center. So there will be 12 coordination number. If you need to find out the number of atoms which are present in the cubical unit cell, we have to cut this particular crystal in such a way that only some part of that will be present in the cubical unit cell. So if I look at each corner atom, that is contributing around 1/8 portion to the cubical unit cell. So here we have 8 cornered atoms and each is contributing 1/8 portion. So 8 into 1 by 8, that is equal to 1 atom. In case of body center, again we have 8 corner atoms, each contributing 1 by 8. When you cut this particular crystal, the body centered atom will remain as it is. So we have 1 body center, so that is contributed entirely. So we have 1 plus 1, that is total equals to 2 atoms. In case of face center, we have 8 corner atoms, so that will be contributing 1 by 8, plus we have 6 face center and each of this 6 face center contributes half of the atom, so multiplied by half, so it's 1 plus 3, that's equals to 4 atoms. Now let us talk about the relationship between the A and R. A is something we are assuming the age length of that particular cubical unit cell, and R is a radius of that atom. So if you talk about the relation between the A and R, we can see this age length is contribution of the 2 radius. So here A will be equals to 2R. In case of body centered atom, the radius and that particular relation can be derived in such a way that if we assume certain triangle in this case, let us assume the triangle which is present at the side of this particular cube. So this is A, B and C. This is right angle triangle. This distance is nothing but A, this distance is A, and let us assume the diagonal of that particular triangle be B. So in the triangle ABC, we have B square is equals to 2A square using Pythagoras theorem. But now if I assume one more triangle over here, which is consisting of diagonal of entire cube, let us assume it as C, and this is age length. So this triangle, I am calling this as triangle ACD, in which C square is equal to B square plus A square. But we have B square is nothing but 2A square. So 2A square plus A square, that will become 3A square. Therefore C is equal to square root of 3A. But now we can see this C is nothing but 4R. Therefore 4R is equals to root 3A. So A is equals to 4R by root 3. That's a relation between the A and R for the body centered cubic cell. Now in case of the FCC, we have to assume only one triangle. So let us assume this triangle to be like this. So we have this triangle, let's say ABC, right angle triangle, diagonal is B and the age length are A. So in the triangle ABC, we have direct relation, B square is equals to 2A square, but this time we can see B is equal to 4R. So B is equals to root 2A, but 4R is equals to root 2A. So A is equals to 2 root 2R. So we have for SCC A is equals to 2R, for BCC A is equals to 4R by root 3, and for FCC A is equals to 2 root 2R. For the numerical reason, student can also remember that C is equals to root 3A. C is the diagonal of the cube and A is the age length. So we can assume this, if the age length is given, we can calculate the body diagonal of the cube. In case of next part, we'll be talking about some more questions related to this. First of all, we'll be talking about total volume occupied. Now in case of the SCC, we have only one atom in the cubical unit cell, and for spherical atom, the volume occupied is 4 by 3 pi r cube. In case of BCC, we have two atoms, so 2 into 4 by 3 pi r cube, that will become 8 by 3 pi r cube. And in case of FCC, we have 4 atoms, so therefore 4 into 4, that is 16 by root 3 pi r cube. That will be the volume occupied. If you convert this into percentage volume occupied, for SCC it is 47.6%, for BCC it is 68, and for FCC it is 74. If you subtract this from the 100, you will get a total void space that is found to be 54.3 for 52.4 for this particular SCC, then 32 for BCC, and for FCC 26%. In case of density for any cubical cell, you calculate for SCC, BCC or FCC, the rho is equals to Z into M Na upon AQ. That's a formula. Now Z is the number of particles, M is the molar mass of the substance, Na is Avogadro's number, and A is the age length. Here for SCC, Z will be equals to 1 and A is equals to 2R. For BCC, Z is equals to 2 and A is equals to 4R by root 3. And in case of FCC, we have Z is equals to 4 and A is equals to 2 root 2R. So we can use all this formula for the solving numerical based MCQs. So we can talk about, in short, the location of atoms, and we can solve the numericals related to this. If we have corner atoms, it always contributes 1/8 section to the cubical unit cell. Body center atom contributes entire atom. Face center contributes half. Edge center contributes 1/4 and end center contributes again half. Corner atoms we generally have 8. Body center is always 1. Face center is always 6. Edge center we have total 12, and in case of end center we have 2. So let us say we have a numerical. A is present at the corner, B is present at the edge center, and in case of C is present at the face center. What is the formula of the compound? If this kind of numerical comes, then A is present at the corner, so 8 corner atom multiplied by 1/8, that's equal to 1. B is present at the edge center, we have total 12 edge center multiplied by 1/4, that's equals to 3. And in case of C, it's present at the face center, so 6 into half, that's equals to 3. Therefore formula of the compound is A, B3, C3. So such kind of numericals we can solve on the basis of this. Now we'll be talking about the different packing in case of the crystalline solids. This packing can be discussed with respect to different directions or dimensions. We'll be talking about the first one, or one-dimensional arrangement, where we'll assume the particles are arranged along one of the axes lying side by side to each other. So if you assume any of this atom, let's say this, it will be in direct contact with 2 other atoms. So here the coordination number for the one-dimensional arrangement becomes 2. This particular arrangement, if you see, we call this as linear arrangement, where we have a linear arrangement of the particle. Now this linear arrangement of the particle can be considered into 2 dimensions in 2 different ways. Now this one-dimensional layers are arranged on top of each other so as to get the 2-dimensional layer. Now if you look at the first arrangement, these arrangements are arranged on top of each other in such a way that the atom of one layer is in contact with the atom of the another layer. Generally we call this as crest, and we call this as trough, or we can call this as depression. So if you can see here, the atoms are aligned as well as depressions are aligned horizontally as well as vertically. So if we call this first arrangement as A, the second will also becomes A, third is also A, and the fourth is also A. So this kind of packing we call it as AA type of packing. In case of AA type of packing, if you look at the shape of the void space, that becomes square. Assume any one atom, this has been surrounded by total 4 atoms, so we call this coordination number as 4. If I join this surrounding atom, the shape which I am getting is square, that's why this packing is also called as square closed packing. While in case of the second type of arrangement, if this one-dimensional arrangement are arranged on top of each other in such a way that the atom of one layer is in contact with the depression of the another layer. So if we call this one layer as A, the second becomes different, so we'll call this as B. But the third one and the first arrangement is same, so again A, and the fourth one is B. So we call this as AB type of packing, which gives us a triangular void space. But this particular triangular void space, you can see they're pointing alternately upwards and downwards. The coordination number for any atom, if you count, it is 6. And if I join these 6 atoms through their centers, I get a hexagon. So we call this packing as hexagonal close packing. Now to arrange the three-dimensional arrangement, we are going to consider this AA type of packing and this AB type of packing separately. So let us talk about first AA type of packing. Now we can see this AA type of packing are arranged on top of each other in a such a way that atom comes in contact with atom and the depression comes in contact with depression. So again, if first layer is called as A, the second becomes also A, third also becomes A, and the fourth is also becomes A. In two-dimensional layer, it has coordination number 4. So now when I am talking about this, above this atom there is one more atom comes and one atom comes below. So its own layer is surrounded by 4, one atom above, one atom below. So coordination number now becomes 6. This is the coordination number of SCC, that's a simple cubic structure which can be obtained by the AA type of packing, three-dimensional packing of the atoms. Now to assume the AB type of packing, how this will look in three-dimensional. Let us assume this particular part first. We have here one AA layer, that's green colored balls I have shown. On the top of that I have shown a black colored layer of the other atom. We'll call this as B. Why I will call this as B? Now I can see that the atom of the A is in contact with the depression of the B. So we'll call this as AB layer. When you have this kind of AB layer, there are two types of void spaces created. The first void space where the 3 atoms, look at this, 3 green atoms come in contact with one black atom. So 3 green atoms comes in contact with one black atom. Here the void space inside this being surrounded by 4 atoms. So this void space look like a tetrahedral void which is being surrounded by 4 atoms. So coordination number for this void is equals to 4. While in case of this particular atom, we can also see these 3 green atoms are in contact with 3 black atoms. So 3 green atom contact with 3 black atom. So this kind of void space is being surrounded by 6 atoms. So we call this as octahedral void with the coordination number is equals to 6. So overall in the 2 layers of AB packing, we have 2 types of void spaces, tetrahedral void and the octahedral void. Now depending on what kind of void spaces are covered by the 3rd layer, the packing will be different. For example, if the 3rd layer covers the octahedral void of the 2nd layer, the 3rd layer becomes different than the 1st and the 2nd. For example, look at this. This is a layer where the 1 atom in the center will come in contact with the 3 atoms. So 1st and the 2nd layer is making tetrahedral void. But the 2nd and the 3rd layer, 3 is coming in contact with 3. They are making octahedral void. So definitely the 1st layer is different than the 2nd and 3rd layer. So we'll call this as ABC type of packing where the coordination number becomes 12. How 12? 6 in its own layer, 3 above and 3 below. So that will be coordination number 12 and this will give rise to a simple FCC or a CCP type of structure, that is cubic close packing. Also, if the 3rd layer covers the tetrahedral voids of the 2nd layer, for example, if you have an A layer where we have the B layer and A layer making the tetrahedral void with each other. Even the B is making the tetrahedral void with the 3rd layer also. So the 1st and the 3rd layer becomes similar. So we call this as ABC packing. This gives rise to a HCP structure. Again, the coordination number becomes 12. So in case of FCC and HCP, both have the coordination number 12. In case of packing, when I am talking about related to ionic solid, we have to consider it a different way. Because cations and anions have the different sizes. So depending on the charge and the size of that particular atom, we have the different voids being occupied. Now generally we say anions form the structure and the cation occupies the void spaces or in the structure of the crystal array of the anions. We have 4 types of void spaces: trigonal, tetrahedral, octahedral and cubic. Trigonal with the coordination number is equal to 3, tetrahedral with the coordination number is equal to 4, octahedral has 6 and the cubic has the 8. Now if there are n number of atoms in the crystal, always remember T stands for twice, so that will be 2n number of the tetrahedral voids, and O stands for once, there will be n number of octahedral voids in the particular structure. For example, now if we talk about the NaCl, Here Na is plus and Cl is minus. So in the case of the ratio between this cation and anion is 1:1. Whenever the ratio is 1:1, the anion forms this structure. So anion, that is Cl minus, will form the FCC, and since the ratio is 1:1, the ratio is 1:1 for the number of atom and the octahedral void. So the Na plus will occupy the octahedral void spaces of the Cl minus. In case of Na2O, we can see here the ratio is 2:1. So who is 1 here? Oxygen. So the O2 minus ions will form that particular FCC structure, where Na plus, now we have Na plus in the 2 form, that means double number. So double number are always tetrahedral voids, so Na plus will occupy the tetrahedral voids of that particular crystal. Now we have a formula CaF2, where the ratio is 1:2. So this time the calcium is expected to form the FCC, and since the fluorides are double, they will occupy the tetrahedral void spaces in case of the calcium 2 plus FCC. Cesium fluoride have a ratio 1:1. So again anions, that is Cl minus, forms the structure. But in case of cesium, since it is 1:1 ratio, it is expected to occupy the octahedral void, but the cesium size is bigger, so it is expected to go in a cubic void. So cesium plus occupies the cubic void, which is exceptional because of its large size. Now in case of ZnS, we have a ratio 1:1, where S2 minus forms this structure. Now since the ratio is again 1:1, it is expected that zinc will occupy the octahedral voids. But the zinc size is very small, so rather than going in octahedral void, it will go in tetrahedral void. But if it occupies the tetrahedral void, the ratio will become 2:1, and we want a ratio 1:1. Therefore, the Zn2 plus occupies the alternate, or we can say 50% of the tetrahedral voids. So we can calculate the ratio of different ionic solids and their packing with respect to whether they occupy the tetrahedral voids or whether they occupy the octahedral voids. We can also find out the radius or a structure of ionic solid using the rule called as radius ratio rule. Generally this rule says that we have to divide the radius of cation by the radius of anion, and we get a certain ratio that we have to match with this table. If this ratio is between 0.155 to 0.225, that will be trigonal with the coordination number 3. If it is between 0.225 to 0.414, it will be tetrahedral with the coordination number 4. If it is between 0.414 to 0.732, it is octahedral with respect to coordination number 6. And if it is between 0.732 to 1, it is cubic void with the coordination number 8. For example, if they have given us the sodium ion ratio radius is 0.95 and Cl minus is 1.81, we can divide the radius of sodium by Cl minus, that is 0.95 divided by 1.81, that comes out to be 525. This comes in the range of octahedral, so it is expected Cl minus will form this structure and sodium will go in its octahedral void. Also, for the ionic solids, we can also find their radius and the age length relation. If this particular structure is BCC, then R plus plus R minus is equals to root 3a by 2, while for FCC, it is R plus plus R minus is equals to a by 2. So we can use these two formulas to find out the relation between A and R for the ionic solids. The next part is the defect in the crystal lattice. Usually the crystalline solids have a perfect structure due to the slow crystallization. But by any means, if some defect occurs, these defects are classified into two types. First we have a line defect, and second one we have a point defect. The line defect is generally due to the irregularity due to a complete line of the particles. While here, if there is some defects or related to some constituent atoms, we call this as point defect. Point defect is further classified into two types. One is stoichiometric and another one is non-stoichiometric. Let us talk about stoichiometric. When I talk about stoichiometric, if certain defect occurs related to certain number of cation, the similar number of anions will also experience the defect. That's called as stoichiometry. Now if you look at this particular defect, we can see here some atoms are missing. So we call this as vacancy defect. When this vacancy defect occurs with the ionic solid, that is if certain number of cations are missing, then same number of anions will also be missing. So we call this a stoichiometric vacancy defect, commonly known as a Frankel defect. Sorry, it's not Frankel, it's called as Schottky defect. In case of the interstitial, we can see there is some atom missing from here. But this atom has not left the crystal, rather than that it has came in the void space. So this is a defect where the atom loses its original position and comes in the void space, which is also known as interstitial space. So we call this as interstitial defect. If this interstitial defect occurs with the ionic solid, this we call it as Frankel defect. In case of the third defect, we can see some of the atoms being substituted by the other foreign particles. So we call this as impurity defect. Now this impurity can occupy the original position of atom or can go in interstitial space. So if it goes in the original position of the atom, we call it as substitution. For example, like brass, where some of the copper atoms being substituted by zinc. While in case of interstitial, we can have example of a steel where in the crystal of the iron there is impurity of the carbon, but that goes in the interstitial space. All these defects we have seen, whatever the defects occurs with the cations, the same kind of defects occurs with the anions also. That's why we call this as stoichiometric defect. But if the stoichiometry is not maintained, we call this as non-stoichiometric defect. Now we can see here there are two things can occur. Metal excess, that means now the cations are more compared to anions, therefore we call this as metal excess defect. We can see over here, this is ionic solid where one of the anion is missing. If an ion is missing, there has to be cation missing, but we can see all cations are as it is, only the anion is missing. So we call this as vacancy metal excess defect. Since anion is missing, the nuclear charge won't be balanced, and to make it balanced, electron will occupy the position of that anion. Since electrons are trapped in the crystal, they give particular color to the solid, and hence this kind of defects are also called as F-centered defect. The meaning of F is a farb, the meaning of the farb is color. We can also see in case of the metal excess defect, we can see one cation has came into the interstitial space. So when one cation comes in the interstitial space, we are expecting anion also to be in interstitial space. But anion is not there, rather than that we have an electron over here. So again the metal cations are more compared to anions. So it's metal excess, but this is interstitial defect. Similarly, we have second type, that's the metal deficiency defect, where we have anions more compared to the cations. So here you will find cations are missing, anions are as it is. So this is a vacancy defect. Here the anion came into interstitial space, but cations are missing. So here this is called as interstitial metal deficient defect. Here to balance the charges, one of the cation will be present in its higher oxidation state to make the particular substance neutral in nature. In the next part, we'll be talking about the electrical properties of the substances. In our entire periodic table, we have classified the substances into three types, that's metal, metalloids and non-metals. In case of metals, they are good conductor, metalloids are intermediate, and in case of non-metals, they are bad conductor of electricity. To explain the metallic conduction of these substances, we are going to take the help of the band theory. For that, let us assume the example of magnesium with atomic number 12. So configuration is 1s2, 2s2, 2p6 and 3s2. Now in case of magnesium, when we have a metallic piece, all these magnesium atoms have their inner orbitals, that is 1s, 2s and 2p. They are closely packed. And these inner orbitals of the magnesium, that is we are talking about 1s, 2s and 2p, these inner orbitals, they overlap with each other. When the atomic orbitals overlap with each other, they turn into the molecular orbital, these molecular orbitals go on merging with each other till their energy gap becomes same, and they give rise to a band which we call it as the valence band. Now we are left with the outermost band, that's a 3s. The 3s orbital of these atoms, they merge together, they turn into the molecular orbital, and they give rise to a conduction band. Now we can see the valence band has more electron, conduction has less number of electrons. Generally what happens when the magnesium is present in its metallic bond form, it becomes Mg2+, that it loses the electron from the outermost shell. So it becomes 3s0. And these electrons are loosely embedded in the particular crystal. Now in the case conduction band has 0 electron, valence band has more electrons. So when the electron jumps from the valence band to the conduction band, they become available for the conduction of electricity. So as easily the electron jump from the valence to conduction give rise to the electrical property of the substance. In case of the metals, the gap between the valence band and the conduction band is very small. That can be achieved very easily, and hence metals are good conductor of electricity. But in case of metalloids, this gap comparatively increases, but this band can be decreased, or this gap can be decreased by means of heating of that particular solid. In case of non-metals, this gap is very large, which cannot be even overcome by means of heating, and hence they are insulator even at high temperature. Metalloids can be improved by a process called as doping. Now when I am talking about the doping, they are doped with the different elements of the different groups, and the electronic differences are created. Generally we say this particular metalloids belongs to the group 14. So if we dope it with the impurity from group 13, then when I am talking about the group 14, there will be more electron rich compared to the 13. So we have added impurity in the group 14, which is electron deficient in impurity. So this will give rise to the semiconductor, which is P type of semiconductor. So P type of semiconductor can be obtained by having the impurity having number of electron, that is 3 electron in the outermost shell, because we have a group 13 over here. We can also dope group 14 with the group 15 elements. Now compared to the 14, 15 elements will be electron rich. So this will give rise to the N type of semiconductor, and N type of semiconductor will have the impurity with the 5 electron in its outermost shell. So doping of the semiconductor can be done by adding impurity from 13 or 15 depending on which type of semiconductor is to be created. The next property that we'll be discussing about, that's a magnetic property. Electrons in the substance, they act like a tiny magnet. They have its own spin motion, and this spin motion gives rise to the magnetic property of the substance. If we have the electrons, these are paired up in the substance, then one electron moves in clockwise direction and one is anti-clockwise direction, so they cancel spin of each other. The magnetic property of substance will be 0. So the one which is having 0 magnetic property, we call that substance as diamagnetic, because all electrons are paired up over here. Since this substance originally has no magnetic property, if we keep such substance in an external magnetic field, definitely it will be weakly repelled by the magnetic field. But suppose electrons are unpaired, then this particular tiny electron will have its own magnetic field. If we keep such a substance in the external magnetic field, this substance will be weakly attracted by the magnetic field, and we call this substance as paramagnetic, where electrons are unpaired, which act like a tiny magnet. In case of third one, that's category called as ferromagnetic substances. In case of ferromagnetic substances, those substances shows the permanent magnetism even in absence of the magnetic field. For example, the substances like Fe, carbon monoxide, etc. Also we have nickel, they have the number of unpaired electrons, but these unpaired electrons, they show a radial magnetic field giving permanent magnetism to the substances. So we call this as ferromagnetic in nature. So depending on the magnetic property, we can classify the substances into diamagnetic, paramagnetic and ferromagnetic substances.